I'd like to present the feasibility of using hydrogen as a solution for decarbonizing Australian vessels. So this presentation is based on our Blue Economy CRC project, Hydrogen Powering of Vessels. The research lead is Mr. Andrew Harris, and I'm the postdoc in this project. My supervisor is Associate Professor Peggy Chen. It's Peggy. Yeah. If you are interested in this project, you can have a look at our project website, and you can download our phase 1 report. So today, we are going to talk through 4 parts. Firstly, we'll talk about why we use hydrogen as a marine fuel. And second, we'll review the onboard hydrogen technologies. And third, the most interesting part of the presentation is a case study for an offshore wind crew transfer vessel using hydrogen. We'll build this conceptual design for this vessel. And finally, we'll discuss some issues and summarize the presentation. First, why hydrogen? The driving force behind using hydrogen is the decarbonization. As you can see, Australia has set a target to achieve net zero emissions by 2050 and to reduce emissions by 43% by 2030 compared to 2005 levels. So Australian domestic maritime sector should align with these targets. Currently, the emissions from domestic maritime sector have been remained around 2 million tons over the past 2 decades, around 2 million tons. So if we want to meet the targets of Australian total decarbonization targets, we need to reduce the emissions from 2 million tons to 1.3 million tons by 2030 and reach zero by 2050. Maritime sector is considered hard to abate sector. So we need to carefully select alternative fuels and energy sources. So what options do we have? That is the question. So let's look at this. We reviewed these alternative fuels and energy sources, the greenhouse gas emission reduction potentials. So the dots here represent the life cycle carbon intensity. So we can see from this figure that HVO, hydrotreated vegetable oil, which is a biodiesel, produced from used cooking oil, and green hydrogen, green electricity are our options. But HVO, the production, scaling up the production is very difficult due to lack of feedstocks. And using green electricity, we have to use a battery. We know that battery is too heavy for most vessels. So green hydrogen has a role to play. As we know, in recent years, there are a lot of arguments around hydrogen. Some people support it, some people against it. Recently, I read 2 books. The viewpoints from these 2 books are completely opposite. So who do we believe? As engineers, we need to speak with our practical engineering studies. So this is why we started this project. Firstly, let's evaluate hydrogen from energy trilemma perspective. The 3 sides of the triangle are sustainability, supply security, and affordability. We have talked about the sustainability. Here we focus on security and affordability. In terms of supply security, let's do a simple math. In Australian domestic maritime sector, the total diesel consumption is around 0.65 million tons per year. If we convert this diesel to green hydrogen 100%, we need 0.23 million tons per year. So that means we need to have 2 gigawatts of electrolyzer and 4 gigawatts of renewable power generation. Is it possible in Australia? If we look at Australian renewable energy targets and hydrogen strategies and pipeline projects, we can see that it's not a problem at all. And then let's look at the cost. According to Cicero, the cost of hydrogen dispensed by refilling station in Australia could range from 6 cents to 13 cents per megajoule. If we compare this cost with diesel, today's diesel price is 5 cents per megajoule. So hydrogen price is much higher than diesel. But at low scenario, 6 cents versus 5 cents is very close. So today we can say that it's time to do some study on the feasibility of using hydrogen on vessels. From technical viewpoints, using hydrogen on board has a lot of challenges. The biggest challenge is hydrogen has a very low volumetric energy density, even though hydrogen has a very high mass energy density. So you can see the volumetric density of hydrogen is lower than all others alternative fuels, but it's higher than battery. What does this mean? If a vessel uses fuel oil, we consider the volume and weight of the fuel to be 1 unit. Using hydrogen, liquid hydrogen, the space we require on board is 4 times of fuel oil. And if you use compressed hydrogen, it will be 7 to 13 times the space required, subject to different pressures. So even though the shortcomings, many countries have already begun building or retrofitting hydrogen-powered vessels. To date, there are more than 40 experimental hydrogen-powered vessels or boats in the world. And most of the vessels, more than 90%, are small vessels, less than 50 meters long. So this is highly relevant for Australian domestic fleet. According to MSR's data, we can see there are more than 7,000 domestically registered vessels. 97% of the vessels are less than 50 meters long. And these vessels are quite old. More than 50% are over 20 years old. So in the next few years, a lot of vessels will be replaced with new ones. So it's an opportunity for us to put more zero-emission vessels into the fleet. Hydrogen can play a role in this. So this is why we do this study. So second part, let's review onboard hydrogen technologies. We did a preliminary technology readiness level assessment. We used 9 scales from 0 to 9. 0 is idea, 9 is full commercial application. For energy conversion, currently, PEM fuel cells are mature and have become commercialized. Internal combustion engine are under demonstration, so we give it a level 6 to 7. And solid oxidation fuel cells is under development, so we give it 4. Hydrogen storage, compressed hydrogen are mature. As we know, a lot of hydrogen-fueled cars have been used in the world. In particular, in Korea, South Korea, today there are more than 30,000 hydrogen-powered cars on South Korea road. And bunkering, so the compressed hydrogen and liquid hydrogen bunkering have been demonstrated around the world. So today, if we want to build a hydrogen-powered vessel, the feasible solution is palm fuel cell plus compressed hydrogen. Currently, there are 3 commercially available palm fuel cells. They are Canadian Ballard, Dutch Nasdaq, and Japanese Yanmar. The maximum power of single module is 300 kilowatts. It's quite small. And for high pressure hydrogen cylinders, type 4 tank attract more attentions because it is a carbon fiber wrapped plastic liner tanks. There's no hydrogen embrittlement problem, and it's lightweight, and its safety performance is quite good. And bunkering. A lot of bunkering operations have been domesticated. As we see, this picture is an onshore hydrogen bunkering station in China. And this video shows the bunkering worker is connecting the electrical force to the manifolds on board. And this picture shows a truck-to-vessel bunkering in the UK for offshore wind cruise transfer vessel. This vessel used a dual-fuel internal combustion engine. Dual-fuel means diesel plus hydrogen. And this project is interesting. It's a Japanese boat. The design adopts a changeable hydrogen storage skid. When the vessel docked, the skid can be easily changed to save bunkering time. So with these developments, so we can say we need to do some study for Australian vessels because this development have given us confidence in exploring hydrogen. So the third part, currently we are doing some conceptual designs for hydrogen-powered vessels. So here I'd like to share with you ongoing conceptual design. It is an offshore wind crew transfer vessel. As we know, Australian offshore wind industry is emerging. 3 offshore wind zone areas have been declared and more have been proposed. So this vessel, we assume, will be working for Northern Tasmania offshore wind farm. The base port will be Burnie Port. It is 40 kilometers away from this area. This is the reference vessel. The original design of this crew transfer vessel is a diesel-fueled crew transfer vessel. She is 22 meters long, and this is the GA of this vessel. It's a catamaran. So first step, we need to calculate the power demand of this vessel. We already know that engine output of this vessel is 736 kilowatts at full speed. So we can calculate it out to the propulsion power, which is 707 kilowatts. So we use this propulsion power to work out the fuel cell output power, which is 826 kilowatts. The interesting part is that the original design, the vessel can store 5.7 tons of diesel. It can run the vessel for 40 hours. After evaluating the space available on board vessel, only 200 kilograms of hydrogen can be stored. It can run only 4 hours, 126 kilometers. So this is an embarrassing number. How to overcome this? We proposed to use 2 changeable tank skids. We put these tank skids on the navigation deck, and each skid has 12 high pressure 700 bar cylinders. And when the vessel docks, these skids can be easily changed at the port. And the skid can be refueled at a nearby hydrogen production plant or refueling station. And skate can be transported with trucks to the port. The advantages are we can save bunkering time. If we bunker these two skates, it will take more than 2 hours. But if we change the skate, it can be done within 15 minutes or 20 minutes. And we don't need to build very expensive hydrogen bunkering stations in ports. And we don't need to have bunkering manifolds on board, which can save a lot of space. And we designed the hydrogen power system like this. We designed 2 independent branches. If one branch has problems, the remaining one can still continue to work. And we also designed the battery pack. The battery pack can be worked together with the fuel cells. And it also can make as a booster to make the fuel cell respond quickly when in the variable operating conditions, because fuel cell response time is quite long, maybe 2 to 3 minutes. And we designed the PID of the fuel gas supply system. You can see the skates are connected to the vessel headlands through the flexible hoses and quick connect disconnect couplings, as you can see in the 3D image. And in a confined space, we need to use double wall pipe in pipe, according to the class rules. And power equipment for diesel system is quite easy: main engines, gearboxes, and generators. But for fuel cell system, we need to have fuel cells, battery packs, switchboard, motor, and gearboxes. That means more equipment means more complicated system. The vessel design is very sensitive to the size and the weight of the system. So we compared the volume and weight between diesel and hydrogen. You can see here on the left-hand side, the volume, diesel power system occupies 13 cubic meters. Hydrogen occupies 28 cubic meters on board. The hydrogen tanks can be put on open space, offsetting some disadvantages. And for the weight, diesel system weight is 11.2 tons, but hydrogen system is 16 tons. So it's much heavier than the diesel system. But in this vessel, we think this is doable. And we also compared the cost. As we can see, the total cost, the hydrogen power system is about 3 times of the diesel system. But for the CapEx, hydrogen system is much more expensive. It's 16 times of the diesel system. So currently, if we use hydrogen, it's very expensive. You know that. And safety is our top concern. So currently, we are doing some CFD simulations to study the behavior of hydrogen dispersion after leakage. So we can see here, if the vessel, if there's leakage from the weak point, if the vessel is still and there's no wind, we can see the gas disperse upwards. Because hydrogen, the density is very low and the diffusion rate is very high. But when the vessel is navigating at full speed and there's against the wind is 6 meters per second, we can see different hydrogen dispersion around the deck area. If there's ignition source, it can catch fire or even explosion. So currently we are trying to design some mitigation method. For example, recently we designed windbreak walls. Let's see the image. It can significantly suppress the gas dispersion. But we are still working on other optional risk mitigation methods. So finally, let's do some discussions. Regulation class rules and the standards are very key, are very important for designing hydrogen-powered vessels. So we are happy to see that in recent 2 years, the gap has been filled. A lot of regulations, many classifications have issued their rules, and a lot of international standards, even Australian standards, are being released. And another very interesting thing is that in our case study, we only consider the fuel cells, but recently we are happy to see there are great progress in the development of internal combustion engine, 100% hydrogen-fueled internal combustion engine. Just 2 months ago in the US, Japanese Yamaha launched a pure hydrogen outboard engine for fishing boat. And just 6 days ago, AN announced that they successfully tested the first 100% hydrogen-fueled two-stroke engines. So if the ICE, internal combustion engines, can become available, I think it's a game changer for the industry, because we don't need to change our ship operation habits. We don't need to change anything, just change the fuel. And on the other hand, in our case study, we only consider the compressed hydrogen. But with the development of other hydrogen storage methods, like liquid hydrogen or metal hydrogen, these methods are more efficient than compressed hydrogen. So that will make the ship design, vessel design, more easier. So finally, takeaways from this presentation. First, green hydrogen is near zero greenhouse gas emission fuel. So it can definitely help Australian domestic maritime sector to achieve net zero emissions by 2050. Due to low volumetric energy density of hydrogen, we have limited fuel storage space on board. So that means we need to increase the bunkering frequencies. So that's like a mindset change. Just like 20 years ago, when we had our cell phone, we had to charge it once a week. But after we have the smartphone, we have to charge it once a day. So it's quite similar to this. And the hydrogen equipment currently is very heavy and very big. So we require more compact design. And today, using hydrogen technology is very expensive. So we need to have some technological breakthrough, like because the fuel cell, with the catalyst, we need to have some noble metals like platinum. So if we can find other catalysts to reduce the cost of fuel cell, that will be helpful. And I think with the scaling up of technology, it will become less expensive. And future technology, internal combustion engine, and more efficient hydrogen storage will facilitate the application of hydrogen more easily. So this is my presentation. Thank you, and I like your opinions on our research. Thank you.